So here's another example of a race condition with the linked list. So a stack may be implemented using a linked list, and this is how we can understand a stack. So suppose we have a stack that contains 4, 3, 2, 1. If we perform a push, that means that this new element will be pushed on top of the list. So now the contents of the stack will be 5, 4, 3, 2, 1. And if we pop, that means that we are removing an element that is on top of the list. So suppose we have 4, 3, 2, 1 on the stack. If we perform a pop, then this 4 will be removed from this stack. So this stack may be implemented using a linked list. So we have the pseudocodes here for pushing and popping elements. And we will show in the next slide how to understand this code. Okay, so our problem is what if these two threads simultaneously do pop and push? Or in other words, what happens if one thread calls pop and another calls push at the same time? So this is the um, source codes for each. So we have for the pop, so essentially what happens in the pop is we have a temporary variable TMP that points on the head or the top of the list, and then we will assign the pointer of a list to the next na element. So that is, this will point to this element now. And then we set this next of this temporary na variable, the pointer into null. So that means that we are essentially removing this one. So we have performed the pop na operation. So this element is already moved. While push is that we are going to have a new node element and then new node element, and then which points to the, which we have a new node, and then that will point to this, to the top of the list, okay? And then we will be pointing, and then the new pointer of the list will be lm. So now we have added a new element on the top of the list. Okay, so anyway, the problem here is what if there is some context switching na nangyayari. Okay, thread 1 will perform at some time and then gets preempted, and then thread 2 will take its turn, and so on until both of the threads complete its execution. Okay, so this is how we can visualize it. So we have this linked list, and this is the head of the list. And then we have the null here, which indicates that that's the end of the list. Okay, so thread 1 executes first. So we have a TMP, or temporary, that points to the head of the list. Okay, so it points to this node. And it gets context switched, and the thread 2 will execute. And it will execute this code. So we have a new node lm, and it points to the list. Okay, so its next pointer points to the top of the list, right? And now it gets switched again, and thread 1 will run. And then in this case, the list is equal to the next pointer of the list. So yung next ng list, kasi dito nakapoint yung list, so yung next niya ay dito, yung next na element. Okay, and now it gets switched again. Now we set that the list is equal to lm. So this list will point to the node lm. Okay, so now this list points to this. So now yung head ng list natin ay, or yung list na yung linked list na natin ay nagko-contain na ng 4, 1, 2, and 3. Okay, and we are done with this lines of codes for the push. And then balik naman kay thread 1. Now we point the we set the next na pointer of the TMP into null. So essentially, yung itong TMP will be pointing to null. Alright, so now it's been removed from the list. So now, yung mangyayari is, supposedly, kung push siya, so dapat it should be 4, 1, 2, 3. But in this case, naging null na dito. Okay? So erroneous yung result ng code. Alright? So pag pop naman sana, yung maging list mo sana ay 2 and 3. So meaning dapat nandito yung list mo. Right? O yung top ng list mo. But pag push naman, it's supposed to be 4, 1, 2, and 3. But in this case, nag-null siya dito. Right? So mali yung result. So that's these examples highlight the critical section problem. And this is how we can define the critical section. So it is a piece of code that assesses a shared resource that must not be concurrently accessed by more than one thread of execution. Okay, so a piece of code that accesses a shared na resource. Right, so kung going back dito, ano yung shared resource natin? It is the list. Okay, list yung shared resource. And unfortunately, this definition is misleading. So this implies that the piece of code is a problem. So in fact, it is a shared resource that is the root of the problem. So again, in this example, nag-share sila ng resource, which is the list. All right. So race conditions lead to errors when the sections of codes are interleaved, as shown in the previous examples. So for example, we have these two processes, and they are interleaving. Okay? Or may context switching na nangyayari every now and then. These errors can be prevented by ensuring that the code executes atomically. So in other words, you are executing these lines of codes like a single na indivisible na unit. So magko-context switch ka after these lines of codes are done executing. Okay, so read, add, store, and then dun ka lang magko-context switch, and then read, add, store, etc. Okay. Or this can also happen. So if yung process P yung nag-start na mag-execute, so read, add, store, and then followed by read, add, store, etc. Okay. In other words, to avoid race conditions, the execution of critical sections must be mutually exclusive. Or they cannot run at the same time. At most, one process can be seen at the critical section at any time. So this is how we can view it. So we have a do while loop that will keep on running while it is true. And we have an entry section. For a certain code, we have an entry section, and we have the critical section and the exit section. Okay, yung critical section, this is the part wherein the code uses a shared resource, right? So what happens in the entry section? So it controls the entry to the critical section and obtains a lock on necessary resources. Okay, so meaning pag nasa entry section ka na, this will be may locking na nangyayari on the necessary resources, and that specific na process will be using the resources, no other na resources. Okay, so once na nag-exit na, it eliminates the lock of the resources and informs the rest of the team that the critical section is now completed. So meaning, yung shared resource na yun might be used by another na process kasi nag-exit na siya. Again, yung pag nasa critical section ka, that shared resource will only be used by one specific na process and cannot be used by other na processes. And that resource can only be used by another process once mag-exit na yung isang process. Right? So this is how we can view it. So we have, let's say, two processes, A and B, that are interleaving. Okay, so we have, let's say, the A enters a critical region, meaning malalock yung necessary na resources, and A acquires that resource. Okay, and at this point, B attempts to enter the critical region, but then the B is blocked. Kasi nga, B is blocked because A is still using that resource. And now, done na si A, so it will be unlocked and A leaves the critical region. And ito na yung entry point of B. So now B enters the critical region, and then so this resource again will be locked. Okay, and then no other process like A cannot use this resource. And once B leaves its critical region, then it will be unlocked. Then A can use that shared resource again. Okay. Although implementing this must satisfy some requirements, and there should be mutual exclusion, there should be a progress, and there should be a bounded na waiting. So when we say mutual exclusion, that means that no two processes may be simultaneously inside the critical regions. And we have shown here how we can do that, right? And also there should be a progress, and no process running outside the critical region may block other processes. And then for the bounded na waiting, so no process should have to wait forever to enter its critical na region. So there should be no deadlock or starvation. So that means na interleaving your process. If A runs for some time, then it means that B should be able to run critical to enter its critical region for some time also. Okay, not waiting for forever in order to get its turn. Okay, so the critical na section problem is to design a protocol with which processes can be used to cooperate and ensure mutual exclusion, or that, in other words, no two processes can run at the same time. In the no two processes can use the same shared na resource in a critical na region. Okay, so that's what we mean by mutual exclusion. So how can we then design the entry and exit points to satisfy the above na requirements? Okay, so we will discuss that in the next slides.